I had some examples for you all to try of the derivatives of exponentials. So maybe I'll refresh our memory a little bit of what we did last time. The formulas for derivatives of exponential functions that you need to know are this one. The derivative of a to the x is a to the x times the natural log of a. Not a very complicated formula as these things go. And there's, of course, a, remember, is called the base of the exponential function, and the a is just a number. And depending on whatever number it is, you know, that number goes here and here in the answer when you take the derivative. There's a special number called e, and the formula for e is simpler because the natural log of e is 1. That's sort of the definition of e. The derivative of e to the x is just e to the x. You don't need this other part because in the case when a equals e, this other part equals 1. And so it doesn't need to appear in the formula. So these guys are what you're going to use in all of the examples where you have to take the derivative of an exponential function. So for example, I will just refresh our memory. I have some for you all to try, but if it was just something like derivative of 10 to the power x, you just literally plug into the first formula and there's not much to it. You get 10 to the x natural log of 10. That was using the first formula there. And then that ln of 10 is just a number, which if you, for some reason, want to know what that number is, you would have to plug it into your calculator. You can't do these ln in your head. Almost never. We're going to talk a little bit more about that, later today. So that's the derivative of something like 10 to the power x. What if you have something a little bit more interesting in the exponent? So maybe I'll just say as a little sidebar here, if the exponent has more stuff inside, I mean not just an x, but some kind of other thing, a formula, rather than just plain x. So that if the exponent has more stuff inside, you must use the chain rule. That's what we do when you have stuff inside of another thing. You must use the chain rule. And remember how you do the chain rule is you take the derivative and leave the complicated stuff on the inside, but then separately you multiply times the derivative of the stuff on the inside. So for example, if we had something like derivative of 8 to the power 3x squared plus 7x, how about that? This would be, again, I'm going to use the first formula in the box because it's a 8 and that number is not e, so you can't use the second one. You only use the second one when it's e. If it's any other number, you use the first one. And so, plugging into the first formula here, I get a, which in this case is 8 to the power x, but in our example, instead of just x, it's all of that stuff. So I'm going to get all of that stuff times ln of 8. So this much of it is just using the formula in the box, right? Using 8 for a and 3x squared plus 7x for x. But then, as I said on the sidebar there, if the exponent has more stuff on the inside, you must use the chain rule, which means we do the derivative as usual, leaving that stuff on the inside, and then separately I multiply times the derivative of the inside, which is 6x plus 7. So this part is derivative of the inside. Right? So this is what you got to do if your inside of the exponent has more complicated things in it. All right? And then, of course, there are other variations on this. So it may be that you have to use the product rule or the quotient rule at some point. For example, if I had something like derivative of 3x squared plus 8x plus 1 times 3 to the power x. This one would be a product rule because I have a product, right? Those two things are being multiplied together. So in this case, we have to do the product rule. And I hope you all remember the product rule. It is the first thing like it is. That's 3x squared plus 8x plus 1 times the derivative of the second thing, and the derivative of 3 to the power x is the first formula in the box up there. No longer visible, but it's 3 to the x ln of 3. So that's the first part of the product rule. The first thing times the derivative of the second thing, and then I go plus the second thing like it is, which is 3 to the x, times the derivative of the first part, which would be 6x plus 8. So this was, because of that right there, we had to do the product rule. All right. So those product rule, quotient rule, and chain rule, really, they are going to come up all the time inside of other kinds of problems. Any thoughts about that? If not, I got some for you all to try. If this doesn't make sense, as I'm walking around, I'd be happy to say something about it. All right, how about, see if you can try these here. The first one is easy. Each one, just take the derivative. And I got one more. All right, I'll write these formulas over here again. Eventually you should memorize this. I mean, if you do it enough, you'll remember them naturally, I think. That's the box. All right, see what you think, and I will come around and see how you're doing. Feel free to chat with the folks around you if there are any.
So it's like this one here. Does that work? Keep the same at first, and then separate it times. Actually, in this case, you don't need the product rule, even though there's a multiplication. Because this is a no. Yeah, because that's a constant coefficient. So the 3 just stays here. Do the derivative of that. Yeah, like all you really need to think about is the derivative of this. So you just leave the 3 as a multiple on the front.
The 3 is just a constant coefficient in front. And so when you do the derivative, the 3 will just be a constant coefficient. So you basically can ignore the 3, although it appears in the answer.
This is good, but you need to use the formula part because you have more stuff on the inside here. The chain rule, which means you do this, which is correct. product rule is not necessary because this is a constant coefficient, which means you can just leave a constant in front. So that actually that's the answer. If you have, it's not illegal to do a product rule, but you should, when you're doing the product rule here, you do the derivative of the first part, the derivative of 3, zero. So take the coefficient, this part of the product rule should be this thing. That should be the product.
But when it's a constant multiple, you're better off not doing the product, just doing this. Doing all right? This one's great.
This close, what's this? 20 times? And it should just be. This 3 is not part of the exponential product. Really should be a little more.
It's the natural log of 7, which, yeah, you would just leave it like that, unless you wanted to plug it into your calculator. Okay?
Yeah, I think
That's good.
I think I must have spun up the first time at 21, 3 times 7.
Yeah,
Where's
you
the-
can't do 3 times 7. Because
Where's
it's,
the, yeah, where does the 3 go then?
3 is just,
Just like times.
just a coefficient. Yeah.
Yeah. But I still
Where's
think,
the-
I still wouldn't put it in front of log, right?
Another 3?
Yeah, I would, right? It's just, I do this bottom one too.
You're doing the product rule, right? Yep. So it should be the first thing times the derivative of the second thing together. Plus the second thing times the derivative of the first thing. Yeah, nice straightforward.
I'm supposed to do the first thing. That makes sense.
Yeah. So now that's right. So let's just pull that. Thank you. All right.
Yeah.
Okay.
These are different practice problems.
Oh, from last time. Yep. All right. Still doing okay? Still doing all right? This one's great. This one here you do the product rule. So, but I think it looks like you just took the derivative of each part.
Yeah, because I thought this was outside.
Yeah,
It's a
it's a product. Still doing good?
Yeah, I'm just trying to figure out this one.
So this one, I would say the 3 is just a constant coefficient. So it will just stay as a constant coefficient. Like there'll be 3 at the beginning of the answer, but otherwise it does not affect anything. And this one, which is
So does the 3 go on the
in the front of the answer. Still doing good? Yeah, pretty good. Should be square root of 1.
Oh, yeah.
All right, how about we chat about these? I know not everybody's finished, that's all right. It looks like the first few, most people did great. So, I have to get rid of this for now. So the first one, 5 to the x is, this you just plug directly into the formula. It's 5 to the x, natural log of 5. The next one looks slightly weird with the 3 there. You may be tempted to just at the very beginning multiply 3 times 7, but you shouldn't do that. It's because of the order of operations. You should do the exponent first and then multiply by 3. And constant multiples do not combine well with exponents in this way. So you cannot just turn this into 27. The 3 is a constant coefficient in front of everything, which means when I take the derivative, it's just going to stay like a constant coefficient in front of everything. So my answer will begin with the 3 times whatever, and then the 3 has almost nothing to do with anything. Although it doesn't go away, it just stays as a 3. as a constant multiple. Anyway, the derivative of this now is very similar to one we just did a moment ago, like this one here. So I go, the formula in the box is 7 to this, minus 7 up there, times ln of 7. So that much is the derivative of the 7 to the power x squared minus 7. But then because that stuff is not just x in the exponent, when I use the formula in the box, I have to do the chain rule, which is to say multiply by the derivative of the inside, and that is 2x. So this came from the derivative of the inside of the exponent. So I hope that's what you got. Any thoughts about that one? All right. The next one. This one is a pretty typical chain rule problem where you have the thing on the inside, which is x to the 5 minus 5 to the x, and then the outside is the exponent to the 5th power. So I do the power rule on the outside, like so. Now to the 4th power, that's the derivative of the outside, and then times the derivative of the inside. The derivative of the inside, x to the 5 becomes 5x to the 4, minus 5 to the x is an exponential function, so I do the formula for a to the x. I think most people got that one. Anybody got questions about that? This is a chain rule overall. All right. The next one is a product. So you got to do the product rule. 4 to the power x is the first part, and x squared plus 1 is the second part. So doing the product rule, it is the first part, 4 to the x, times the derivative of the second part, which is 2x, plus the second part, the second part is x squared plus 1, times the derivative of the first part would be 4 to the x ln 4. That's from the formula for exponential functions. That's what you got. And the last one is a quotient rule, because I can see the quotient there, and it has an e to the x. Remember, the derivative of e to the x is e to the x. So I'm going to do the quotient rule here. I hope you remember the quotient rule. It's the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. So the bottom, x to the 4 plus 3x, times derivative of the top. The top is e to the x. The derivative of e to the x is e to the x. So that's the bottom times the derivative of the top. And now I go minus the top is e to the x times derivative of the bottom is 4x cubed plus 3. All of this divided by the bottom squared. X squared, like that. And I think that is what I got. Any questions about that one? All right. Thank you for your participation in these problems. So this is the end of what I want to say about derivative of exponential functions. It is most interesting when combined with the chain rule and product rule and quotient rule. All right. Great. Let's get on with it then. So for the remainder of today, I want to talk about logarithms. This is a topic that I think maybe you talked about in high school. I don't know, or in a pre-calc class. Some people do this and some people don't. It's super important, at least historically speaking, in the history of mathematics. Logarithms were a huge kind of breakthrough in the 1600s, which allowed people immediately, once we understood logarithms, it allowed people to do things. There are tricks with logarithms for multiplying big numbers together, like without a calculator in the 1600s, that was super important back then. Those tricks are not so important today just because we have calculators and such to do them. But from a theoretical point of view, actually logarithms still come up all the time. And they are still useful. It's just we can use calculators to work with them now. Anyway, I'm going to pretend like you don't know anything about logarithms. If you've already seen this before, then you may find this easy. Although, in my opinion, the idea of logarithms is kind of complicated no matter what. So it might be a good thing to see it again if you've seen it before. Sorry, I'm fixated on this. Is this screen broken too? There's like a thing. It looks like a piece of tape. Can you see that up there? Just put a piece of tape on it. Nothing on that one. All right. Okay, so here's the idea of logarithms. It is that logarithms sort of go together with exponential functions. So we have, for instance, many different exponential functions with different bases. Exponential functions, everybody knows, have different bases. You know, the base, remember, is the sort of like the big number down there, like 2 to the x, or 5 to the x, or 10 to the x, or e to the x. E is a special base, which has nice properties as far as calculus goes. These are all different exponential functions with different bases, right? In the same way, there are different logarithms with different bases. So every exponential function kind of goes together with a logarithm, and the logarithm is sort of the inverse or the reverse of an exponential function, but I'll get to that in a moment. But anyway, I will just say every logarithm has a base, and so we write, actually there's no such thing as the logarithm. There's actually many different logarithms. There's like the one which goes together with the exponential function 2 to the x is written like this. And this is called, when I see this, I say the log base 2 of x. There's a base 2 logarithm, there's a base 5 logarithm, etc. Log base 5 of x. 10 to the x goes with, the log base 10 of x. Actually, the log base 10, for historical reasons, has a special name. This is referred to as the common log. And it has a special way of writing it. It's written as just log, without a little number written. So when you see log with no base indicated, you assume the base is 10. The common log was one which, like when logarithms first were kind of invented or discovered in the 1600s, they used the base 10 log most of the time for computing with. Nowadays, there's nothing really special about it anymore because we can do all of this on calculators anyway. And anyway, there is also a logarithm associated with e to the x. This is, you could write it like the log base e of x. But this one also has a special name. This is called the natural logarithm. The natural logarithm, and it's written ln of x. So this is the one that we have been talking about at least a little bit. Nowadays, the natural logarithm is still viewed as very important. What they call the common log is not so important anymore. It was important because it was the one that people used to do computations in the old days before calculators. But now that we have calculators, your calculator probably has a ln button on it, and it probably also has a log button, which does the base 10 log. We are basically never going to use the base 10 log in this class, although there's nothing wrong with it, but it's not really special for anything. The natural log is special for reasons which we'll talk about. It's because it's based on e, and we already know that e is special as an exponential function. All right. Anyway, what does this all mean? Like I said, these logs go together with the exponential functions, and any exponential formula or expression or whatever, I'll say any exponential equation can be rewritten in what we call the logarithmic form. As follows. There's nothing too fancy about this, but you just have to kind of know where everything goes. So this is the exponential form. I'm trying to write 2 to the power x equals 8. This is the exponential form of that statement. But you can write it the other way around, instead of using an exponential, using a logarithm, and it looks like this. Log base 2 of 8 equals x. This is the same thing, but written in logarithmic form. These two equations, they mean the same thing, though. So the first equation says 2 to some power equals 8. The second equation says the log base 2 of 8 equals something. And those two equations are the same. They are interchangeable. All right? And this tells you the meaning of the logarithm. So what does that mean? So log base 2 of 8, it means this is a number. It means this number such that when you do 2 to some power equals 8. So it means 2 to equals 8. What is the exponent that you need to do in 2 to some power to get an answer of 8? All right? So it's the exponent above 2 to make the answer 8. And can anybody say what is that exponent? This, when you say it this way, you can just kind of guess the answer. 2 to what power equals 8? What'd you say? The third, yes. I was expecting her to say 3. She said third, and it didn't make any sense to me at all. I don't know why, but yes, that is correct. The answer is 3. 2 to the third equals 8. So log base 2 of 8 means 2 to what power equals 8? And the answer is 3. So sorry. Log base 2 of 8 equals 3. That's because if your friend at lunch asks you, why is it true that log base 2 of 8 is 3? The answer is because 2 to the power 3 equals 8. And those are just two ways of saying the same thing. 2 to the power 3 equals 8. It's the same as saying the log base 2 of 3 equals 8. It means 3 is the exponent that you need to make 2 to what power equal 8. The answer is 3. All right? So in this way, you can do some logs just like by hand on paper. And like that's an example where you figured out the log base 2 of something on paper. How about, let's try, I got a few of these for you all to try too. This is not hard, really. You just have to know where everything goes properly. Log base 3 of 9 equals what? All right? The way to think this through, in my opinion, is try to rewrite this as an exponential format. So this is in the logarithm format. As an exponential statement, this would say 3 to what power equals 9. And you have to just remember how to rearrange things properly. All right? This little 3 here is the base. It's the base of the logarithm. So when you write the exponential format, it becomes the base of the exponential function. And then you just have to remember sort of this number here ends up over there on the other side of the equal sign. This is how you translate the logarithmic version into the exponential version. But anyway, once you write it in the exponential format, you should just be able to guess the answer. And what do you say? 2, yes. Or the second, if you prefer. Yeah, so this right here must be 2. Right? And so that means log base 3 of 9 equals 2. It's because 3 to the power 2 equals 9. That's what the log means. I don't know if this seems confusing. In my opinion, it is slightly confusing. It would be nice if there was just like a formula for the log that you could just plug the number into, but it ain't like that, all right? You have to rearrange the logarithm in terms of an exponential and then sort of guess the answer or see what fits in properly to make it all work out. How about, I got another one, how about log base 2 of 16 equals what? Rewriting as an exponential format, remember where everything goes. The base of the log becomes the base of the exponent. So here the base of the log is 2, which means what I'm about to write with an exponent has 2 as the base. It's 2 to some power equals 16. This is how you rearrange everything. And then what is the power? 2 to what power is 16? I don't know if you know these off the top of your head, but I mean, if you're desperate, you could just write down the various powers of 2. You get 4 and then 8. 2 to the 4 is 16. So the answer is 4. That number right there better be 4. So log base 2 of 16 is 4. All right? If you really know what you're doing, you can kind of do all of this in your head, although I wouldn't suggest trying it at first. But you know, if somebody asks me what's the log base 2 of 16, I can say 4 immediately, because this is mostly just in your head anyway. It's just a matter of rewriting it into a format where you can then guess the answer. All right. Now there can be a few somewhat weird things that happen when you're doing these. How about log of 1,000? First of all, you have to remember, this is sort of a technicality that I said a few minutes ago, but what does it mean when I write log with no base on it? What is the base in that case?
10.
It is 10, right. When there's no base indicated, you assume that the base is 10. So this, you imagine there's actually a 10 here. And then, to write this in exponential format, it says 10 to what power equals 1,000. And 1,000 is 10 to the power 3. And so this is... the answer is 3. This is why the log base 10 was in common usage, is because it's kind of, it is representing how many digits are in this number, if you like. It's one less than the number of digits in that number. And so if you give me a number, say, I don't know, 2,317, I can tell you the log, the base 10 log of this is something between 3 and 4. It's probably like a little bit more than 3. I don't know any more than that, but that kind of thing is possible to do with the base 10 log. I don't really care about that, but that's why it was useful in the old days before people had good computers. All right, I got 2 more slightly weird ones, and then I have some for you all to try. How about log base 5 of 1? Writing this in the exponential form, the base is 5. So this will say 5 to what power equals 1? Any thoughts? 0, she says. Yeah, I hope you remember, anything to the power 0 equals 1. And so if you want to fill in the exponent here, the answer is 0. So that means log base 5 of 1 equals 0. And I will just point out, actually, that problem really has nothing to do with the number 5. This is not a special property of the number 5. It's true that any number to the power 0 is 1. And so actually, this is not only true with log base 5, this is a general property of all logarithms. Generally speaking, no matter what the base is, any base, the log of 1 is always equal to 0. This is a true fact in general. Why is that true? It's because whatever a is, a to the power 0 equals 1. And that's the same way, that's the same as saying the log base a of 1 is always equal to 0. All right? So the log of 1 is always 0. Great. Something good to know. One more slightly weird example. How about the log base 2 of 1/4? Again, I'm going to rewrite this in the exponential format. It says 2 is the base. 2 to what power equals 1/4? This one is slightly weird just because it's a fraction there. And remember, a few moments ago, I wrote down a bunch of powers of 2. 1/4 did not appear in this list. Is there a power of 2 which equals 1/4? You got an idea?
Isn't it 1/8?
1/8.
Is it a negative number?
1/8 is a good idea, but not if you use a fraction inside the exponent.
Yeah.
I think you're suggesting that 2 to the power 1/8 is 1/4. That's not quite true. A fraction in the exponent represents a root. So if you said something like 2 to the 1/2, you get the square root of 2. That can't give you this. There is something though. What can you use in the exponent to get a fraction? You can use a negative number. That's the meaning of a negative exponent. Is a negative exponent gives you 1 over something or other, right? And
It's negative 2.
yeah, in order to get 1/4, you want to use negative 2 as the exponent. So this 1/4 is 1 over 2 squared. And so 2 to the minus 2 power is 1/4, right? And so the answer to this one is negative 2. Log base 2 of 1/4 is negative 2. All right. So you can get a negative answer of when you're doing a logarithm. The answer can be negative. This will happen if, generally speaking, log base whatever of a fraction will be negative. So if you ever see a fraction here that you're trying to take the log of, you should expect to use a negative exponent, which makes the answer negative. All right. All right, I have some simple logs for you to try out. These ones are, very similar to what I was doing a moment ago. So see if you can find each one. If you know what you're doing, these are quite easy, although if this is unfamiliar to you, it is, I would say these can be also quite confusing. So beware, perhaps. All right, see what you think about that.
Writing 16 equals 2. Yeah, really, like, if you want to be very clear, I would write X equals.
Okay.
That's the.
Okay.
How's it going? 2, I agree, yeah. Alright. Yes, great. This should say 2 to the power equals root 2. Alright. Yeah, that's good.
Doing okay?
2. I like that.
No, you like this one.
So it means 2 to some power equals square root of 2.
Good.
I might have just missed this one.
Yeah. This is square root of 1.
Oh, yeah, so, that's right.
Square root of 1 is 1.
Yeah.
We just put 1, but that's not right. The question is about 2 to some power equals 2.
I thought, it's like, I don't know how to get the square root there.
Isn't it possible to think of the square root as an exponent?
Yeah.
No sense. Other than- Is that a question mark?
Yes.
Your answer?
Yeah.
So that if you, yeah, I mean, I would think of it in this way, so if you rewrite this, it would
Yeah.
be, the base is 10. No, this is 10, but when it's not
Yeah.
written, it's 10.
Yeah.
So the question is 10 to what power equals 1?
Oh, so 2.
It's 2.
Okay.
I think people are feeling pretty good about these. Can we chat about these ones? If you feel good about these, then that's great. I mean, these kind of don't really get any more complicated than these. So log base 4 of 16, this means if I were to represent this, let me just move these guys out of the way here. If I were to represent this as an exponential, it would say 4 to what power equals 16, and 4 squared is 16, so the answer is 2. So log base 4 of 16 is 2. And the next one is also 2, because 9 to the power 2 equals 81. So this one, for the same reason, is also 2. What about log base 3 of 27? That one you think as 3 to what power equals 27? And the answer is 3, because 3 squared is 9, and then 3 to the third power is 27. So log base 3 of 27 is 3. I think everybody did that all right. And then what about log of 100? Remember, log with no base written means log base 10. And so this, in exponential form, looks like 10 to what power equals 100? And the answer is 2. 10 to the 2 is 100. So log, the common log of 100 is 2. All right. Any questions about those so far? Those are the, I suppose, the easier ones. These ones are not much harder, although they're very slightly weird. So this first one you think of as 2 to what power equals 1/8. Anybody get this one? What'd you say? -3, yeah. Because it's a fraction, I know the answer is going to be negative. It's got to be, I have to think of 1/8 is 1 over 2 to something, right? And the answer is it's 1 over 2 to the 3. So this is -3. Log base 2 of 1/8 is -3, because 2 to the -3 power is 1/8. And then finally, log base 2 of √2. So this means 2 to what power equals the square root of 2? And I hope you remember, the square root is the same as a 1/2 power. So the answer that goes in the little exponent there, the question mark, it should be 1/2. Because 2 to the 1/2 is the square root of 2. I hope everybody agrees with that. This, in order to make this work out, should be 1/2. So that means the log base 2 of √2 is 1/2. All right? These are the logarithms. In the old days, people had giant books full of the values of logarithms. Rather than using a calculator, somebody figured all the values out by hand once and then wrote them in a book. And then everybody just, if you wanted to calculate the logarithm of something, you look it up in the book. The logarithm is also the basis of how a slide rule works, which was super important for centuries before modern computing. I will just say, these logs you can do by hand, but I will just say something like most random logs can't be done by hand. Like if your friends at lunch say, "Hey, you know all about logarithms?" Okay, like what's the log base 3 of 8? Your answer is I don't know that one, because this means 3 to what power equals 8. And the answer is, well, 3 to the 1 is 3, 3 to the 2 is 9, but 3 to what is 8? There's kind of nothing. I mean, 3, it's not any number that you know, at least. There is such a number. It's just a really weird number that you would have to work out on a calculator. So this right here, you can't just guess the exponent in this example. I would say if I had to say, I would say it's a bit less than 2, right? Because 3 to the 2 is 9. This is a little bit less than that. So whatever that log base 3 of 8 is, it's a little bit less than 2, but you can't really say in any more detail than that. So typical logs you cannot do by hand. You have to kind of get lucky, and that is the thing you're taking the log of has to actually be a power of the base that you're talking about. All right. Anyway, can we say a little bit about the natural log? So the natural log uses e as the base. And e is just some weird number, some specific strange number with, decimal values that go on forever, kind of like pi. The natural log uses e as the base, and basically you can never do this one by hand because e is such a weird number. Right? So if I said something like, what is the natural log of 15? If I turn this into an exponential format, you use the base of e. This means e to what power equals 15? And my answer immediately is, I don't know, because e is a weird number, and there's no way that I could guess the exponent in this formula here. All right? So this we can't do by hand. And this is why, you know, that's why I said last time, if you really want to know what ln of a number is, you just have to type it into your calculator. Although there are two exceptions to this. Sometimes we can do it by hand. So except, I will say, what about ln of 1? For the same reasons that I said before, ln of 1 always equals 0. This is because the log of any base of 1 is always equal to 0. And the reason why that's true is because e to the power 0 equals 1. So this is since e to the power 0 equals 1. All right, so that's one value that you can do by hand. You can also do something like, what is the natural log of e to the power 3? Well, if I write this in its exponential format, the natural log uses base e, so it means e to what power equals e to the power 3. This is weird, but this thing, which is what I'm taking the log of, becomes like the right-hand side of this exponential formula. E to what power equals e to the 3? Anybody think you know? This seems like a stupid trick question. It has an appropriately stupid answer. The answer is 3. E to what power equals e to the 3? The answer is 3, is what you put here if you want these two things to be equal. So it's 3. So it is a fact that the natural log of e to the 3 is 3. This is not a special property of the number 3, so generally the natural log of e to any power x is equal to that power x. So this is basically the only situation in which you can actually do the log by hand, the natural log, I mean. If you are already talking about a power of e, then the natural log equals that power. All right? This is what I wanted to say about the basics of the natural log. There are several formulas about how logs work. There's formulas about, like, what is the log of, a times b. It's like there's a formula for that. It's equal to the log of a plus the log of b. Although those formulas, we are not going to require them much at all in this class. But there is one important formula that we are going to use all the time with logarithms. One important tangent property. This is true actually of any log, but I'm just going to write it for the natural log. It is log of anything with an exponent in it. By log, I mean natural log. Sometimes I just say log when it says natural log because I'm a sophisticated mathematician and I never really talk about the other kinds of logs. The natural log is the nicest one. Anyway, the log of a to the x is equal to x times the log of a. This is a basic property of logarithms, and from our point of view in this class, this is the most useful fact that there is about logarithms. And the reason that this is useful, this lets you move the variable out of the exponent. Because, inside that box, on the left side, the variable is inside of an exponent, but on the right side, the variable is not inside of an exponent anymore. And so if you want to solve an equation where the variable is inside the exponent, you can use this sort of logarithm trick. It is the basic usage of the logarithm in sort of real life word problems. So for example, we can do, how about a problem like solve for x in here, 8 to the power x equals 15, all right? how can you solve this formula for x? X is inside of the exponent, so you can't like, I don't know, you might be tempted to say, can't I just like divide both sides by 8 to get the x by itself? The answer is no. You can't divide by 8 because this is not multiplication, this is exponents. What do you do instead? You use logarithms. This is the classical situation when you would use a logarithm. And what I'm going to do is do ln on both sides. It looks like ln 8 to the x equals ln 15. And then I do the thing in the box up there. Sorry, it's scrolled up. Log of something with an exponent, the exponent can come down to the front as a coefficient. So I'm going to do that over here on this side, right? I have this log of something to the power x is equal to x times the natural log of that number by itself. So this is x natural log 8 equals natural log 15. And now I can solve for x by dividing. All right, that was the point of this. My job in this problem was to solve for x. So I go x equals log 15 divided by log of 8. And if this was, on a test or something, you would just leave your answer like that because you can't do any more by hand. This just for your information, I typed this into my calculator just to see what I'd get. I got 1.302 something something. All right, that's not something you can do by hand though. So I would expect on your tests in such a question to leave your answer like that. Do the log on both sides in order to bring the exponent out of the, or in order to bring the variable out of the exponent. That's the trick here. All right. And I will say just a little cautionary tale about doing problems like this. Make sure to isolate the exponential part first. I'll tell you what I mean by that. You're going to do the log on both sides with the intention of bringing the exponent down, but you have to isolate the exponential part first. Here's what I mean by that. How about, let's just do another one. Solve for x here. Let's say 5 plus 3 to the 2x equals 80. All right. I said, make sure to isolate the exponential part first. You cannot, at this point, just take the log on both sides because the left side is not just the exponential thing. It also has that 5 plus in there, which is going to screw it up. All right. I do not want to take the log yet because the left side is too complicated. It has to be just an exponential thing on one side. And then I'm going to take the log. So what can I do before that? I say isolate the exponential part first. This is the exponential part that I'm talking about. And I want to get rid of this 5 over here. And the way to do that would be subtract 5 on both sides first, right? So I'm going to subtract 5 on both sides first. It becomes 3 to the 2x equals 75. This is what I mean by isolate the exponential part first. And now I can continue. Take the log on both sides, the natural log, of course. It says ln 3 to the 2x equals ln 75. And then do my little trick, which is the exponent comes down to the front as a coefficient. So it's 2x natural log of 3 equals natural log of 75. And now we can just solve this for x. We would divide by 2 and also divide by natural log of 3. And we get x by itself on one side. So it says like this. I divide both sides by 2 and also by natural log of 3. And we get just x by itself. All right. I got a couple more, and then I think we'll be done for today. Can we do something like this? But I would like to do a cute little word problem. Can you believe it? These logarithms actually are super useful in word problems, any kind of thing which involves exponential functions. So if you recall from last time, I had a made up word problem here about a pandemic spreads, and the formula that I was using was f of t equals 50 times 1.01 to the power t. This is the number of infections on day t, right? If you know how to use logarithms, you can answer important questions like, for example, how long until 100 people are infected? How long until 100 people are infected? Using this formula, now you may be just looking at this, you may be tempted to simply plug in t equals 100 and say what the answer is. Actually, that is not the way to do this, because remember, t represents the day. T is the time, right? This question is not about using t equals 100. That would be if I asked you how many people are infected on day 100. That would be you plug in time 100, t equals 100, and tell me the answer. This is how long is it, that is to say, what is the time which makes it so that 100 people are infected. So really what I'm asking you is, which t gives me f of t equals 100, right? That's what the question is. It's not plug in 100 for t, it's actually set the function equal to 100 and then solve for t, all right? So that means we need to do 50 times 1.01 to the power t equals 100, and then solve for t. That's what I'm talking about here. Which is the t which makes that thing equal 100? And how do we do that? You do that using the log. It's because, you know, it has to be involve a logarithm because I see the variable is inside the exponent. And the only way to get the variable out of the exponent so that you can solve for it is by doing the natural log on both sides, and then you move the exponent down. Now, I will say, again, you must first isolate the exponential part, which is this. We need to isolate that part before taking the natural log on both sides. If you take the natural log right now on both sides, the 50 there will mess it up. So any suggestion, how can we isolate that part? Yeah?
Divide by 50.
Divide both sides by 50. And this you can do in your head pretty easily. 1.01 to the power t equals 2, right? I divide both sides by 50. 100 divided by 50 is 2. And then from there, we do the old thing with the natural log. You take natural log on both sides. So it's natural log 1.01 to the power t equals natural log of 2. And then inside of a log, the exponent can come down and become a coefficient. It says t ln 1.01 equals ln of 2. And then I can solve for t, just divide the ln 1.01. So this is ln 2 divided by ln 1.01. All right. And again, if this was on a test or something, I would expect you to leave it at that because you can't simplify that. You can't do those ln's by hand. I typed this into my calculator just for fun. I got 69.66, which means that, you know, midway through day 69 is when you hit 100 people infected. And I hope you can believe that this is useful kind of a thing to be able to do in the real world. This is a very natural question that you would want to be able to answer. You have to use logarithms in order to do it. So this means 100 people infected, let's just say by day 70. Since it's like 69, day 69.6 is the precise moment when the 100th person gets infected. All right. Excellent. I got just a couple for you to try, just using this ln trick to solve for something in the exponent. It'll probably only take a moment. The first one is very straightforward, and I will say leave the natural log in your answer. This is how I'll say it on a test. If you want, you could plug it into your calculator to get a real number for the answer, but I don't care so much about that. I got 2 of them here. All right, see what you think. You should be doing the natural log on both sides and then bring the exponent in.
This is a little backwards. The rule is ep09 is based on
That's good. Actually, this is
Just the phone.
this is upside down. Just when you solve for x, you divide by log of 5.
So it's the other way.
Goes on the bottom. Actually, this is the fractions upside down. Because you divide that.
What do you do with the first 2?
You shouldn't leave it. You need to sort of isolate this by itself before you do the log. All right, can we talk about it? I know not everybody's done, but I also know you probably want to leave. You didn't even want to stay this long. Let's just try. So as I was going around, everybody did great on the first one. You do the log on both sides. Log 5 to the x equals log of 37, and then you bring the x down. X log 5 equals log 37, and then you divide by the natural log of 5, and it looks like this. Natural log 37 divided by natural log 5. Several people wrote the fraction upside down. I'm not sure why, but it should be this way around, because this natural log of 5 gets divided over to the other side, so it goes downstairs over there. Right? Great. Everybody did that one fine. The next one. So this one is slightly more complicated because of this 2. You need to isolate the exponential part first. So I'm going to begin by dividing both sides by 2. And it becomes 3 to the 5x plus 1 equals 10. You've got to do that first. If you leave the 2 in there and take the log with the 2 in there, it messes everything up. Anyway, now we take the natural log on both sides. ln 3 to the 5x plus 1 equals ln of 10. And then the exponent inside the log comes down to the front. This is the whole point of doing the log on both sides. It looks like that. I saw a lot of people got this far and then weren't really sure of what to do, but I hope everybody is good with this so far. This is a little weird looking, but how am I going to solve for x now? By the way, I hope you wrote these parentheses here. If you left them out, it's not quite right. And also, in my opinion, putting the parentheses here gives a suggestion of how we're supposed to proceed from here. I need to solve for x, but x is sort of surrounded by all of this nonsense. You need to send all of this other garbage to the other side. And so the way to begin that process would be to divide both sides by the natural log of 3 to put this guy over here. So when I divide both sides by ln3, it's like this, right? So it now says 5x plus 1 equals ln10 over ln3, like that. Can we continue to solve for x? Any thoughts? What should I do next? I got to get just x over here.
Minus 1.
-1, yeah. Subtract 1. So it's 5x equals this. Okay, and then divide by 5, and that's it. So the answer is going to look kind of messy over there, but it is natural log of 10 over natural log of 3 minus 1, all divided by 5. How you like that? Maybe not too much, but I mean, this is just a number. If you have a calculator, you could, if you want to, just type this into your calculator, and whatever that is, that's what x is. All right, that's all.